In December 2019, China notified the World Health Organization of several cases of human respiratory illness, a disease later named COVID-19. The virus causing this disease is known as severe acute respiratory syndrome coronavirus 2. The disease spreads through small droplets that are expelled from the nose or mouth when a person with COVID-19 coughs or exhales. Therefore, standing close to someone who is infected can put you at risk. These droplets can land on your hand and be transmitted through something as simple as a handshake, if afterwards you touch your eyes, nose, or mouth, the so-called T-zone. The virus is known to survive on different types of surfaces, so touching these contaminated surfaces and then touching your T-zone brings a high risk of infection. What we know so far: the coronavirus is spherical in shape, and its genetic material is encapsulated by different types of proteins. Some of the key structural ones are spike S protein, the most prominent feature of coronaviruses from where they get their name, then M, or membrane protein, and the so-called envelope protein.
Assalamu alaikum. I am Nazmul Shahid, lecturer in physics in Boshal Cadet College. Boys, I think that you are safe and sound in your home. Due to corona pandemic, we take our classes online, and I believe that very soon we will meet again. Today I discuss, that is chapter number 5, and the name of this chapter is Electromagnetic Induction and Alternative Current. And this is the first class of these chapters, and the learning outcomes. By the end of today's class, cadets, you will be able to explain number 1, that is electromagnetic induction, magnetic flux, and Faraday's law of electromagnetic induction. Number 2, Lenz law. Number 3, self-inductance, that is self-induction. Number 4, that is the last, mutual induction. For going to discuss electromagnetic induction, firstly I show you a animation. This is the primary coil and this is the secondary coil. Here we give some alternative current in the primary coil, and with the help of induction in the secondary coil they are generated current. And we know that this is nothing but the Faraday's experiments, we can prove it. So from the background of information of the electromagnetic induction, I say something. In 1830, Joseph Henry find out that if the electromagnetic flow is turned on or off, there is a flow of current in the coil vaporing in iron brace when it is kept between poles of an electromagnet. On the other hand, Faraday thought the electric field becomes dynamic because of the flow of the charge, and this dynamic electric field creates an electromagnetic field. In 1831, Faraday noticed that upon passing a current through the one coil, a momentary current was induced in the other coil, and this is called electromagnetic induction, and the produced flow is called induced current. So this is the process in which we produce current with the help of primary coil. Now I discuss magnetic flux. Magnetic flux through any surface is the number of magnetic lines of force passing normally through that surface. It can also be defined as the produce of the area of the surface and the component of the magnetic field normal to that surface. if the surface area is ds and the perpendicular direction is n, that is normal, and the acting magnetic field B make a angle with normal is theta, then the component of unit area direction is B cos theta. Then we know that d phi, that is magnetic flux, is equal to B into ds. There is a vector components, and if we goes to scalar components, then B into ds into n vectors. The direction of ds is along to the normal to the surface, and n is the unit normal vector that we discuss later. D phi is equal to B into ds cos theta. If the surface area is A, then we can return that phi is equal to B vector dot A vector, that is B A vector into n vector. Then we can write that phi is equal to BA cos theta. So this is the normal equation for magnetic flux. You must be memorized. Phi is equal to BA cos theta. For positive flux, magnetic flux is positive if theta, that is 0 degree is less than is equal to theta is less than 90 degree, and 270 degree is less than theta is less than is equal to 360 degree. For zero flux, we find when theta is equal to 90 degree and theta is equal to 270 degree. And negative flux, 90 degree is less than theta is less than 270 degree. So flux is maximum when theta is equal to 0 degree, and in this case we can written that magnetic flux phi is equal to B dot A, that is BA. So phi is equal to BA cos theta. Magnetic flux across a coil can be changed by changing, that is the condition for increasing the magnetic flux. Number one, the strength of the magnetic field B will be increased. Number two, the area of cross section of the coil A if we increase. Number three, the orientation of the coil with the magnetic field theta, or number four, any of the combination of the above. Note that here the magnetic flux is a scalar quantity. The SI unit of magnetic flux is Weber or Tesla into meter square. Physics unit of magnetic flux is Maxwell. 1 Maxwell is equal to 10 to the power minus 8 Weber. Magnetic flux per unit area is called magnetic flux density or strength of magnetic field or magnetic induction, that is B. Now we discuss Faraday's experiments. There are two experiments, we already knows that, and you must observe the animation. When a magnetic, there is bar magnet, and we know that two poles of bar magnet is NS, there is north and south. It comes to the coil, then the pole of N is produced, the same side of the coil is N here, and the opposite side is S. So there is a current is producing in this coil. Again, if the bar magnet is coming, S poles come to the coils, then the nearby side is produced S poles, and the direction of the current is also be opposite from the previous one. So you see here the coming of the current is south, and out of the current is north. Here also be the current comes from south and goes from north. The direction of the current is always same, but the producing of the poles of the coils is not same. When the bar magnets n side is coming, then the coil produce n side, there is n pole. If the S side is coming, then the current is produced S poles in the coil. And here also we taken a bar magnet and produce current in the coil. Magnetic flux link with the coil changes relative to the position of the coil and the magnet due to the magnetic lines of force cutting at different angles at the same cross section area of the coil. And the observation is number one, the relative motion between the coil and the magnet. Number two, the induced polarities of the magnetism in the coil. Number three, the direction of current through the galvanometer and hence the deflection in the galvanometer. Number four, that is induced current, that means electromotive phase EMF is available only as long as there is relative motion between the coil and the magnets. And note here, number one, coil can be moved by fixing the magnet. Number two, both the coil and magnet can be moved towards each other or far away from each other. That is, there must be a relative velocity between them. Number three, magnetic flux link with the coil changes relative to the position of the coil and the magnets. And last one, current and hence the deflection is large if the relative velocity between the coil and the magnet and hence the rate of change of flux across the coil is more. So kids, you must be careful about the observation and note. Here I also show you a animated clips. Here I show you when the bar magnet comes to a solenoid, that is a coil, then the direction of the current is on side, and when the bar magnet is comes far away from the coil, then the direction of the current is another side. Then Faraday's experiment number 2, for a closed circuit. For a closed circuit, when the circuit is closed, then the direction of the current is on side, and when the direction is current is passing, the direction also be opposite to the currents. And observation, when the primary circuit is closed, current goes from 0 to maximum value. During this period, the current induced changing magnetic flux across the primary coil. The changing magnetic flux is linked across the secondary coil and induced EMF, that is the electromotive force, is in the secondary current. So this is for the closed circuit, taking a one circuit and producing current in the second circuit. This is the second experiment. First experiment is taking a bar magnet in a closed circuit and produce a current, and the second experiment taking one coils and producing current in the another coils. Induced EMF, that is hence the deflection in galvanometer, lasts only as long as the current in the primary coil, and hence the magnetic flux in the secondary coil will be changed. When the primary circuit is open, current decrease for maximum value is 0. During this period, changing current induce changing magnetic flux across the primary coil. This changing magnetic flux is linked across the secondary coil and induce current EMF in the secondary coil. However, note that the direction of current in the secondary coil is reversed, and hence the deflection in the galvanometer is opposite to the previous case. Faraday's law of electromagnetic induction, that is a law, that is first law. Whenever there is a change in the magnetic flux linked with the circuit and EMF, and hence the current is induced in the circuit. However, it lasts only as long as the magnetic flux is changing. And the second law, the magnetic, that is magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linked with a circuit. That means E is proportional to d phi by dt, that is E is equal to k into d phi by dt, that is E is equal to d phi by dt if the values of k is equal to 1 and normal values of E is equal to phi 2 minus phi 1 by t, where k is a constant and units are chosen such that k is equal to 1. So now we are going to introduce you the Lenz law. The direction of the induced EMF or induced current is such that it opposes the change of that is produced. So boys, you must be recall that both of the animations we show you when the bar magnet is coming, the current is produced, that is when the n pole of the bar magnet is come to the coil, then the same side is produced n poles. So we know that the properties of magnetism, the same poles are repulse each other and opposite poles are attack each other. By this way, the poles are uh, repulse each other, and this is the law of Lenz law. If the current is induced due to the moment of the magnet, then the induced current in the coil set itself to stop the motion of the magnet. If the current is induced due to the change in current in the primary coil, then the induced current is such that it tends to stop its changing. So it's always time stopping the motion or changing the flux of the EMF current. So Lenz law and the law of conservation of energy. According to the Lenz law, the induced EMF oppose the change that is produce it, and it is such kind of opposite against which will be perform mechanical work in causing the change in magnetic flux. Therefore, mechanical energy is converted into electrical energy such that Lenz law is in accordance with the law of conservation of energy. If there the reverse would happen, that means the induced EMF does not oppose or aid the change, then a little change in magnetic flux would be produced and induced current, which would help the change of flux further, therefore producing more current. The increased EMF would then cause further change of flux and uh, it would further increase the current and so on. This would create energy out of nothing, which would violate the law of conservation of energy. Now the equation of EMF, that is the electromagnetic force, E is equal to minus d phi by dt, E is equal to minus phi 2 minus phi 1 by t, where for n number of turns of the coils, then E is equal to minus n into d phi by dt. Then is the normal Faraday expression for induced current. I is equal to minus d phi by r into dt. Then the experience for charge dq by dt is equal to minus d phi by r into dt. We written that dq is equal to d phi by r. Note that induced EMF does not depend on resistance of the circuit, whereas the induced current or induced charge depend on resistance. So method of producing induced EMF, number one, by charging magnetic field. Magnetic flux phi can be changed by changing magnetic field B, and hence EMF can be induced in the circuit as done in Faraday's experiment. Now I say something about coronavirus. You must stay at home, about touching your face noise without washing your hand. For this reasons, you must wash your hands, and spending time must be 20 seconds, and must be avoid close contact with flu-like syndrome persons. Now we discuss about self-induction and mutual induction. Firstly, self-induction. Self-induction is the phenomena of induced EMF in the self coil due to change in current, and hence the change in magnetic flux in the coil. The induced EMF opposes the growth or decay of a current in the coil, and hence delay the current to acquire the maximum value. Self-inductance is also called inertia of electricity, as it opposes the growth or decay of current. Now the self-induction equations: I is proportional phi, that is phi is proportional to I, and we can written phi is equal to Li, where L is the constant of proportionality and known as self-inductance or coefficient of self-induction. If I is equal to 1, then L is equal to phi. Those self-inductance is defined as the magnetic flux linked with a coil when unit current flows through it. Now we put the values of current electricity. The equation E is equal to minus d phi by dt, or E is equal to minus L di by dt. If dl by dt is equal to 1, then L is equal to E. Those self-induction is defined as the induced EMF set up in the coil through which the rate of change of current is unity. And lastly, we discuss mutual induction. Mutual induction is the phenomena of induced EMF in the secondary coil due to change in current in the primary coil, and hence the change in magnetic flux in the secondary coil. Mutual induction, that is as like of self-induction. Phi is proportional to I, that is phi is equal to m into I, where m is the coefficient of mutual induction, and this is also constants of proportionality. I is equal to 1, then m is equal to phi. Those mutual induction is defined as the magnetic flux linked to the secondary coil when unit current flows through the primary coil. Then the current equation E is equal to minus d phi by dt, that is E is equal to m into di by dt, where di by dt is equal to 1, then m is equal to E. Those mutual induction is defined as the induced EMF set up the secondary coil, where the rate of change of current in primary coil is unity. SI unit of mutual induction is Henry. Mutual induction is said to be 1 Henry when 1 ampere current in the primary coil links magnetic flux of 1 Weber across the secondary coil, or mutual induction is said to be 1 Henry when rate of change of current, that is 1 ampere per second in primary coil, induce EMF on voltage in the secondary coil. Now some knowledge based questions in these chapters or in these topics. Number 1, what is meant by electromagnetic induction? What is electromagnetic induction used for, and what is the principle of electromagnetic induction? What is an example of electromagnetic induction? What is the formula for magnetic flux? What is the magnetic flux and magnetic flux density. What is the Lenz law in simple terms? Some comprehension based questions. How does Faraday's ring work? Why Faraday's law negative? How is flux generated? Some MCQ questions, that is 2 MCQ question. 1 Tesla is equal to, there are 4 options, and I know you must be know about the correct answer. And the second question, electromagnetic force of 10 volt is induced in a coil if current is changed from 0.1 ampere to 0.5 ampere in 1.015 second in that coil. What is the self induction of the coil? And find out or do the mathematics and find out the answer of the 4th options. Now homework that you practice in your home. Now question number X, that is what is meant by electromagnetic induction. Number B, what is fixed flux generated. Number C, if the number of turns of the coil of figure 1 is 100 and the flux of each turn change from 30 into 10 to the power minus 5 wave to 2 into 10 to the power minus 5 wave in 0.04 second, then calculate the induced EMF in the coil. Number D, does the above law obey the conservation law of energy? Give your opinion. And now the question answer session. If you have any question and query, then ask me. After the finishing of today's lesson, I will reply you in dashboard. And more about clear in the topics, I give some video clips, and with these video clips I am sure you must be clear about electromagnetic induction or today's topics. And with this hope, I now should conclude today's class. Thank you all.
Electromagnetic induction. In this lesson, we shall learn about electromagnetic induction. The phenomenon of electromagnetic induction can be demonstrated by an experiment. Wind an insulated copper wire on a paper or wooden cylinder so as to form a coil in the form of a solenoid. Connect the two ends of the coil to a galvanometer and place a magnet close to it. The reading of the galvanometer is 0 when the magnet is stationary. The pointer of the galvanometer deflects towards the right when the north pole of the magnet is moved towards the solenoid. The galvanometer shows 0 reading when the motion of the magnet stops. This proves that as long as the magnet keeps moving, current flows in the solenoid. If the magnet is moved away from the solenoid, current flows in opposite direction in the solenoid. Thus, the galvanometer deflects towards the left. The deflection increases if the magnet is moved away with greater velocity. If the polarity of the magnet is reversed and the magnet is brought close to the solenoid, then current flows in an opposite direction. The galvanometer accordingly turns towards the left. Faraday observed that current flows in the coil only when there is a relative motion between the coil and the magnet. The direction of deflection in the galvanometer is reversed if the direction of motion is reversed. The current in the coil and the corresponding deflection of the galvanometer can be increased by using a strong magnet or by increasing the motion of the magnet. Increasing the area or the number of turns also creates a strong current in the coil. According to Faraday, when there is no relative motion between the magnet and the coil, the magnetic flux within the coil remains constant. so the galvanometer shows no deflection. But when the magnet is moved towards the coil or vice versa, the magnetic flux changes and an EMF is induced in the coil. If the circuit is complete, the EMF causes current to flow through it. Based on his experiment, Faraday formulated two laws of electromagnetic induction. Whenever there is a change in the magnetic flux linked with a coil, an electromotive force is induced. The magnitude of the induced EMF is directly proportional to the rate of change of the magnetic flux linked with the coil. The direction of the induced EMF depends on whether there is an increase or decrease in the magnetic flux. John Ambrose Fleming gave two rules to determine the direction of motion, or the direction of induced current. While the left-hand rule is for electric motors, the right-hand rule is for generators. According to Fleming's right-hand rule, the thumb, forefinger, and middle finger of right hand are stretched perpendicular to each other. And if thumb represents the direction of movement of the conductor, forefinger represents the direction of the magnetic field, and the middle finger represents direction of the induced current. Lenz's law states that the direction of the induced EMF is such that it always tends to oppose the cause which produces it. Lenz's law obeys Newton's third law of motion, which states that to every action there is always an equal and opposite reaction. It also obeys the law of conservation of energy. It states that energy can neither be created nor destroyed. Therefore, the sum of all the energies in the system is a constant. Lenz's law is based on Faraday's law of induction. Lenz's law states that when an EMF is generated by a change in magnetic flux, according to Faraday's law, the polarity of the induced EMF is such that it produces a current whose magnetic field opposes the change which produces it.